Yeah, very happy to be here and tell you about this research. It's something rather recent and I think very exciting. And then when I chose this topic, I had to choose not to tell you about some other stuff. And the other stuff I'm not going to tell you about is this new method where we can extract DNA from air and then use that to look for endangered species. And so we did this at a site here on Zeeland. And in a few hours of monitoring and capturing aerosols that contain DNA from animals, we were able to see about two-thirds of all of the species that have ever been observed at that site. So we're very excited about the possibilities for this, for monitoring endangered species. And we also recently found organic material on Mars, and this matches the isotopic signature that you expect from carbon dioxide photolysis. So it's a carbon dioxide atmosphere. It absorbs sunlight. You get a very strong 13 carbon effect. We predicted that here a dozen years ago. And then NASA sent a mass spectrometer to Mars and they dug up some sedimentary organic material and they found exactly the isotope effect that we predicted in carbon dioxide photolysis. And that really shows that carbon monoxide, the photolysis product of carbon dioxide, that's the building block for building these larger organic molecules that are being found by the mass spectrometer. So happy to tell you about either of those. But the thing I'm really going to tell you about is innovation. And so then I can say that this is a journey that I've been on a few times with a couple of different companies. And the first one was a gas phase method for cleaning air that's really linked with what I'm telling you about today. So I'll get back to this, but basically we disclosed the invention, we had a patent, the University of Copenhagen licensed that patent, first to Infuser, later to Loopertech, and then this company then gave birth to a number of other companies that included Air Labs and Airscape and Dev Labs and Rensair that many of these are going on today. We have a similar story with ambient carbon, where we disclosed an invention, it was patented, and now we have a startup company. There's a new company that just came online this week that is removing waste anesthetic gases. So it's ANECO. And that again is a collaboration between University of Copenhagen and DTU. And we have a new startup called Scale, which is one of our master's degree students who worked with low-cost sensors. And he's now making sensors to use in the fermentation industry. All right, so let's get to work. It is very likely that this summer will be the coldest summer that you will experience for the rest of your life, right? Because of climate change and temperatures are going up. And one of the things you can see is that, for example, we have less ice in the Arctic Ocean, and the Arctic Ocean is now passable for long periods of time. And so you have cruise ships that go from Alaska to Manhattan across the Arctic. As a consequence, most of the nations in the world have signed this Paris Agreement, where we have goals of limiting the average temperature on the planet to perhaps 1.5 degrees. But even though there are good intentions, it doesn't seem like we've seen a lot of action because the greenhouse gas concentrations are going up and the temperatures are going up. So this is showing historically what's happened with carbon dioxide, some ice core data in the early part of this, and then measurement data later on. You see also that the temperature is increasing. And it's very common to put these two graphs together and show that the temperature change is linked with the carbon dioxide change. So if you have more CO2 in the atmosphere, the temperature is going up. That's only part of the story. It's a correlation. It's not the full causation. Carbon dioxide is the main greenhouse gas. It has the largest radiative forcing, but there are a lot of other anthropogenic pollutants in the atmosphere that also impact climate, and methane is the largest of those. And so you see here that methane has about 2/3 of the radiative forcing of carbon dioxide. You hear a lot about CO2, but you don't hear as much about methane. And that's what we'd like to talk about here today. So carbon dioxide going up very steadily in the last couple of generations. Methane goes up in fits and starts, and it doesn't seem to be so stable. Part of the reason for that is that methane has much more diverse sources, but it also has a shorter atmospheric lifetime. So if anything changes in the sources, that shows up more quickly in the atmospheric methane concentration. So you can see that the methane increase stalled for a few years. We had a year with a methane maximum, and then it decreased in the early 2000s, but now it's been increasing very steadily through the recent past. So if you look at the sources of methane to the atmosphere, fossil fuel production and use, we have agriculture and waste, biomass and biofuel burning, wetlands, and then other natural emissions. And so it's much more tied with the biosystem. We have wetlands and biomass that are giving off a lot of methane. And then it might be surprising that there are such large errors in these emissions estimates. And one method might give 737 megatons per year of methane being emitted, and another one might give 572, whether it's bottom up or top down budget. Each of those has ranges. So there's lots of debates about how to understand that, but the best understanding right now is that there are increased natural emissions. Part of this might be because tropical wetlands have become warmer and there's more water going through them. So changes in the hydrological cycle. These two things together seem to stimulate more methane. So it's kind of a feedback where climate change is causing additional greenhouse gases in the atmosphere. Most of the methane is removed from the atmosphere by chemical reactions in the atmosphere. 90% is the hydroxyl radical. The rest could be stratospheric reactions or chlorine atoms. And some is being eaten by microbes that sit in the soil. So it's simply taken up into the soil. All right, the National Academy of Science in the United States put out a major report in late 2024 about methane. They say atmospheric methane is like the ancient minotaur, dominantly human, partly natural, and with more than a whiff of cow breath. And what they'd like to do is encourage control of the increasing methane concentration. They note that during this 12-month period, the average global surface temperature was 1.56 degrees above the historical average. That means that, according to this, we're already breaching the Paris Climate Agreement. So I think it's very important right now. If we contrast carbon dioxide and methane, one thing to notice is that methane, we can control it. You could say that methane controls the rate of warming or the warming that we're going to be seeing in the next few decades. Carbon dioxide, on the other hand, has a very long lifetime in the climate system, centuries, perhaps millennia, and that means that CO2 is controlling the end state. If we want to do something to control the near-term climate change, we have to address methane. It has a 1 decade lifetime in the atmosphere, so if we control the sources, we can see the results in the near term. So this is one of the figures from the report. They're saying that right now we have all of these different sources of methane to the atmosphere. We would like to reduce those, and they say that might not be enough, and so we would need atmospheric methane removal. We've heard a lot about carbon dioxide removal. and direct air capture of carbon dioxide. And in this report, they're evaluating technologies for removing methane from the atmosphere, whether that would be enhanced uptake by ecosystems, or having methane reactors or methane concentrators, or maybe photocatalytic surfaces, or enhanced atmospheric oxidation, where you would enhance the ability of the atmosphere to react with the methane. And in my research group, we're doing a lot of work with two of these. The iron salt aerosol method. I gave a chem talk a year ago about the iron salt aerosol method. And then today, I'll be talking about MEPS, the methane eradication photochemical system that can be used for source control. And we now believe that it can also be used as a methane reactor for ambient concentrations of methane. All right, so if we look at these sources, this is a map of the methane emission sources by concentration. You can see that some of the sources are at 1,000,000 parts per million. So that's pure methane. Maybe it's in a pipeline. You could control the leak, close the leak. You save money and you save methane emissions to the atmosphere. That's wonderful. But there are also some more dilute sources of methane to the atmosphere. You could burn that methane in a flare, but once the methane drops below the combustion limit, it will not burn anymore. And that combustion limit is at 4.4%, so 44,000 parts per million. If the methane goes below that, you could use a high temperature catalyst, similar to the catalytic converter on a car. And using different thermal management systems, you might be able to press those to a limit of a few thousand parts per million, maybe 1,000 parts per million, if you were really good at conserving the heat, because that's an energy input into the system. That leaves 3/4 of all of these sources of methane to the atmosphere with no technology to address them. And that's the main conclusion of this report from the National Academies, is that there's no commercial technology operating regularly below 1,000 ppm of methane. And that's what I believe we have developed here with the MEPS system. So that's what I'll be telling you about. To finish off, I would just like to point out that a lot of countries around the world have signed the Global Methane Pledge. This includes the United States and the European Union and Denmark. You can see 158 countries around the world agree that we need to do something to reduce methane emissions. In addition, a lot of companies have signed on to pledges where they say we're going to reduce methane emissions. One example is the Dairy Methane Action Alliance, put together by the Environmental Defense Fund. And you see that Danone and General Mills and Kraft Heinz, Nestle, and other significant brands, even Starbucks coffee, have signed on to this. This means that they're doing methane accounting and methane disclosure. And the main focus here is on methane coming from dairy, from the cows. And so they want to quantify how much methane that is, and then control how much methane is coming from dairy products. More locally, Arla has made a climate pledge, 30% reduction in carbon dioxide equivalent by 2030, and they want to be climate net zero by 2050. 92% of their greenhouse gas emissions are due to farming, and a lot of that is due to cows and methane. So we're working together with Arla to reduce their methane emissions. And I'm sure the people here have heard about the grön skattereform, where we're introducing a tax on emission of carbon dioxide or greenhouse active gases. There are goals in 2025, 2030, 2035, and 2050, and these are coming very rapidly. So we need a technology that is effective at controlling low concentration methane. And why do we see so many technologies for carbon dioxide, but not methane? As chemists will say, it's because the chemistry is very different. Carbon dioxide dissolves in water. You can make salts out of it. You can make minerals out of it. You can get it to stick to a catalyst. Methane doesn't want to do any of those things. Lowly soluble in water. It has a very low affinity for surfaces, so it doesn't spend much time on the surface of a catalyst. And I think you have to work quite hard because the physical properties of methane are similar to those of neon. All right, next section in the talk is to develop the idea of gas phase pollution control. And this is something that we developed here, that I helped to invent, and that this is a test at the LM Wind Power windmill blade factory in Lunderskov. And they had a large problem with styrene. And you can see there is an 80-meter chimney. So we cut a hole in their chimney. We attached our shipping container, and we removed 96% of the styrene the first time that we turned it on. And this was using significantly less energy than the competing methods. The main competing method would simply be to force all of that air through an adsorbent, use activated charcoal, bind up all of the styrene, and then you could burn it. But there's a very large pressure drop, and so a very large energy input in order to treat the air with activated charcoal. Here, we were doing everything in the gas phase using the hydroxyl radical. This is a test that was done last summer where this is the same technology. It's being used to control the odor from a wastewater pumping station outside of Rotterdam. Right now, they have a very large biofilter that's removing all of those. And here we have a little system, and we demonstrated that it's very effective for removing that odor, including, both the reduced sulfur compounds and the organic molecules that are coming out. But there is a but here. We published a paper. We showed that we're removing all of these things in the treatment system. We don't use very much energy, 3 kilojoules per cubic meter of air. But it says that it's viable for most volatile organic compounds, specifically those with a hydroxyl radical reaction rate higher than about 5 times 10 to the minus 13 cubic centimeters per second. A lot of people asked me, couldn't you use this hydroxyl radical method to treat methane? And the answer is no, because the reaction of methane with hydroxyl radical is too slow. It's the slowest of any hydrocarbon. That's why it has such a long atmospheric lifetime. And we tried increasing the hydroxyl radical concentration in the reactor. We would put in more power, more light, more ozone, but we didn't get a higher hydroxyl concentration because the chemistry had become saturated. And the hydroxyl radicals will react with their precursors. They react with ozone, and they also react with themselves. And so the loss processes become nonlinear and increase with increasing concentration. So could we use chlorine atoms instead of hydroxyl radicals? There might be some advantages. You would use a longer wavelength of light because you'd be photolyzing molecular chlorine rather than ozone as the precursor. You would also save energy because the yield per photon is higher. You'd actually get 2 chlorine atoms for each photon, rather than when you use ozone to generate hydroxyl radical, depending on humidity, but your yield might be around 20%, depends on conditions. In addition, the reaction rate coefficient is 16 times faster for chlorine than it is for the hydroxyl radical. But the most important thing is that these self-limiting reactions are much less of a severe limit for chlorine atoms than for hydroxyl radical. And if you take our course on reaction kinetics, we'll teach you RRKM theory. This is Marcus theory. And it says that if you have a reactive intermediate, the lifetime of that intermediate depends on the number of vibrational modes that you have. And of course, you have many fewer vibrational modes in molecular chlorine than in hydrogen peroxide. So these atoms bounce off one another, and the reaction to form molecular chlorine is much slower. However, if you are going to use chlorine, there are potential issues with the reagents and with the products. And so most of the work that we've done has been to address those issues. So here's the invention. We were granted a patent on this in the United States in April of 2024, and we've applied in many additional jurisdictions. The idea is that we use chlorine as a catalyst to strip the hydrogen off of the methane. This means that we start with salt water and then use electrolysis to make molecular chlorine from the salt water. We get molecular chlorine, Cl2. We photolize that. We use UV LEDs. You can see them here at the end of the reactor. This is looking in one end of the photoreactor. When you do that, you create chlorine atoms. They abstract a hydrogen atom from methane. You get hydrochloric acid. We need to remove that using a water scrubber. And this reforms the salt that will go back to the scrubber and reform molecular chlorine. Molecular chlorine. So the chlorine is a catalyst. We synthesize small concentrations from salt water on site. And then we've succeeded in recovering some of the energy value of the methane, which otherwise you would throw away because there's really no good way to extract methane from air. But here, at the other electrolysis electrode, we're getting molecular hydrogen. And Denmark has a goal of having a completely green natural gas distribution system by 2030. You can sell 2% hydrogen in that gas onto the natural gas distribution system. And this means that there would be a market right there for the hydrogen gas that's being made from the methane. And these are the main energy inputs. So we have electrolysis, photolysis, and hydrolysis for the scrubber to make that process go around. Now, Stanford became very interested in this, and so they built a replica of our reactor. And so this is the reactor in Palo Alto. I was there about 2 weeks ago, and they were able to reproduce our numbers. They'd been doing a lot of research on photocatalysts. And so they had, I don't know, some zinc oxide doped titanium dioxide photocatalysts. The best one that they had found over 15 years of research. That one had a quantum yield of 0.001% for putting in light and removing methane using that light. Our system using gas phase treatment has a quantum yield of 2.4%. So we're many orders of magnitude better than a lot of the competing technologies. Based on that quantum yield, we have a cost of 189 euros per ton of carbon dioxide equivalent when the methane is at 50 parts per million. That's for what we're seeing right now and scaling that up to a barn. But we expect to have a price below 100 euros per ton of carbon dioxide equivalent when we reach commercialization. So going into the system, we have these 3 stages. We have inputs of power and sodium chloride and methane. And the outputs are water vapor, carbon monoxide, carbon dioxide, and green hydrogen. And then we can do an analysis of this. One of the things you should consider is whether you're making any byproducts that could potentially be dangerous or climate active or destroy ozone or something like that. So we've thought very carefully about the potential for forming carbon tetrachloride and these other chlorinated methane species. We predict using modeling that we'll have very low yields of these. And whenever we do measurements in the laboratories, they've been below the measurement threshold. So we have not seen these products, and we don't expect very large concentrations of them. We've tested this system at the research station at Folum. So this is an agricultural research station. They have a biogas plant and cow barns and pig barns. And so for the biogas from the pig barn, we had 80 to 100 ppm of methane. We were using a certain amount of chlorine in the system, and we saw 88% removal of the methane from that air. In the barn ventilation, we were seeing almost complete removal of methane from that air. So that was one test. Now, we're planning to do an installation at a large farm in Indiana. And so we went there in October last year, and you can see some of the cows. There's over 4,000 cows at this facility. And then we went up in the lift and we mounted methane monitors below the roof. And the way this roof is set up is there's a gap along the ridge. And so the air is driven up by convection through that gap in the ridge of the barn. So the cows are here, the air goes up and it goes out through that ridge. And here's our little methane sensing device. And this is because Danone wants to test this. And so Arla sells a lot of milk to Danone, and then they're getting pressure from the customer to make low carbon milk. And so it seems their best option for delivering this low carbon milk. And here's what we see in the barn. And this is using a tunable diode laser spectroscopy, a portable TD-LAS system that is made by DevLabs. This is a startup company from some of our graduates from the Department of Chemistry here. The CEO is Johann Schmidt, and DevLabs made these devices. We installed them in the barn, and you can see that we've got something like 40 ppm of methane. This is in a barn north of Odense. So this is the Hofmannsgave Foundation barn. We notice every time they feed the cows, because it makes a lot of dust, so we see a peak of particulate matter, PM 2.5. And then in Indiana, we're looking at the correlation between wind speed and wind direction and the methane levels. And so sometimes here we're at 60 ppm, maybe 80 ppm of methane in the barn. We did some additional tests of the system at Fulham in the fourth quarter of this past year, and then these are the results. We're very happy about these results. We're operating in this range of maybe 5 to 90 parts per million, and we're removing, between 40 and nearly 100% of the methane in that concentration range. So we demonstrate we can remove dilute methane from the airstream. We do that with a very economic use of the light. So the quantum yield is around 1%. So 100 photons in means that we destroy one methane molecule. And from that number, you can calculate the energy input. How many kilowatt hours of electricity remove how many grams of methane? So in our earlier tests, we were between 2 and 8 kilowatt hours per gram of methane. We're now below 1 kilowatt hour, in some cases at half a kilowatt hour of electricity per gram of methane that's being removed. We're very happy about these numbers. Light is the major power consuming system in the MEPS electrolysis, photolysis, hydrolysis system. But we're using a lot of energy for electrolysis and for the pumps. So if we can reduce that, we'll improve the energy efficiency of the system. We were able to put a mass spectrometer. It's called a PTRMS, or that's the main form of it. We put that onto the barn, and we're able to monitor the odor compounds. And so these are things that smell very bad. They might come from cows and pigs and hydrogen sulfide and indole and so on. And we're removing, 80% roughly of all of these different compounds. And you can see that we're also removing ammonia. And we were very excited about this. Ammonia contaminates the groundwater and causes this over-fertilization of wetlands. And here we're able to remove both the odor and the ammonia and the methane from the barn exhaust air. These are some spreadsheets that mainly Hugo and Morton put together, where you look at a typical barn. You might have 300 cows. They make a certain amount of methane per year, and you have a global warming potential. This is 800 tons of carbon dioxide equivalent per year per barn, and you have a cost of electricity and all of these things. And this is basically how we got that cost per ton of carbon dioxide equivalent that we came out with, that compares, I think, rather favorably. This is for current performance with the Danish carbon dioxide tax. And then at Stanford, they've done a techno-economic analysis of all of the different ways of getting rid of methane. Here we have the thermocatalysts. And so you can see that they have a certain reaction temperature, and you have a certain operating range for the methane concentration. But basically, none of these is working below maybe around 500 parts per million. So there's none of them below and in the range that we need for agriculture, and certainly nothing approaching 2 parts per million. Now, they published that paper before we did our work, and they were only aware of one system that was operating at 10,000 parts per million of methane. And that means that it's climate neutral as far as the light going in, and was not cost beneficial. It was cost ineffective. But now with our quantum yield, we're coming in around 1%. And so we're approaching this green area where we're both cost effective and climate beneficial. All right, heading towards the end, you can compare all of the different methods people have proposed for removing methane from the atmosphere. A lot of them would take very large volumes. So this is 10 to the 16 liters in order to remove 1 megaton of methane per year from the atmosphere. And so this system that we've developed at the University of Copenhagen is definitely in the lead as far as the intensity of the reactor, and also the ability to react with very low concentrations of methane. Some of the surface-based technologies have a very low probability of reaction per collision, and this means that you need extremely large surface areas to address that same goal of removing 1 megaton of methane per year from the atmosphere. In some cases, many times the available surface area of the planet. So we have a lot of work to do. And why does our method work so well? It has to do with the kinetic theory of gases. If you make a chlorine atom, it's thermalized. It's traveling at 1,500 kilometers an hour at room temperature. And this means that it's reacting or colliding with billions of molecules every second. And some of those are going to be methane. We believe that the theoretical limit to this technology would be a 100% quantum yield. We're currently at 1%, so we're trying to scale up and improve that efficiency. And I think I'd like to leave a little bit of time for questions. So I'll say thank you very much for your attention.